Hello, everyone. It's me again, Mr. Younger. This time I'm doing part two of the one-dimensional head-on collisions, and specifically the lecture that was supposed to take place April 7th, yesterday. So this is the second part of that one, and in this case, I'm actually just continuing with the head-on collision. So let me get started by going ahead and just share my iPad screen. Here we go. So if you look at the part one video, you'll discover that I basically use conservation of momentum for a head-on collision and conservation of kinetic energy for a head-on collision, and was able to generate this particular formula as an additional equation that we can use sort of in lieu of the kinetic energy equation. So basically the equation that we found in part one was the difference in velocities before the collision, VA minus VB, is equal to the negative of the change in velocities after the collision. So I'll put it in the same order, but pull the negative out in front so that you see you get VA prime minus VB prime. So that is a new equation, and this one, of course, is only valid if momentum. Actually, I don't want to write that there. Only valid if momentum and, I capitalize that on purpose, and kinetic energy are conserved. So this is an equation. I'll just refer to it in this video as equation one. Now, in addition to that, to actually make use of this and still be able to solve for two variables, obviously you'd have to have two equations. The two variables we're solving for, VA prime and VB prime. So I've got one equation now that takes into account both the conservation of momentum and the conservation of kinetic energy. But we need one more equation, and that other equation that we normally use is, I'm going to call it equation two, and we already worked it out, but basically it's MA VA plus MB VB is equal to MA VA prime plus MB VB prime. So this one only requires conservation of momentum. Only valid if momentum is conserved. Now that didn't get written so well, I'm going to rewrite it because I'm OCD. So these are the two equations. Now I'll show you how we can combine them to get a general solution for all cases. This is typically a problem that virtually every textbook has in it. And in addition to that, your book actually gives it on like page 239 or 240, somewhere around there, gives the actual result and tells you that you can see, I think it's exercise 34 to do it. So this is me trying to explain how to go about doing it. I'm going to first take equation one and solve it for V A prime. So from 1, I get that VA minus VB is equal to VB prime. Notice I've dropped the negative and distributed it through VB prime minus VA prime. Now I'm going to solve that for VA prime, and that gives me VA prime is equal to VB prime plus VB minus VA. So now I can plug that into equation two. So I plug this into two, and what I get in that case is MA VA plus MB VB is equal to MA times VA prime plus VB, or should be VB prime. VB prime plus VB minus VA. So that's the expression that I used for VA prime. And I still have the other term from equation 2, which is plus MB VB prime. So what I'm going to try to do is distribute everything, get all the VB primes on the right-hand side and everything else on the left-hand side. So continuing that process, I get MA VA plus MB VB equals MA VB prime, which I'm going to keep on this side, plus MA VB, which I'm going to move to the other side, minus MA VA, which I'm also going to move to the other side, and then plus MB VB prime. That's already in terms of VB prime, so I'm leaving it where it is. So now I can get MA VA plus MB VB. Now I'm going to say minus MA VB, and that takes care of this one. And I'm going to say plus MA VA, and that takes care of this term. And that's it. All I've got left on the other side is MA VB minus plus MB VB minus. So I'm going to go ahead and factor out the VB minus and write it as MA plus MB times parentheses VB prime. So I'm just about ready to solve for VB. I should get some more terms common on the left-hand side. So for instance, I know I have a MAVA and another MAVA, so that's going to be 2MAVA. And I also have a plus MB minus MA. All that's going to be multiplied by VB, and then that's equal to MA plus MB, parentheses VB prime. So now I am ready to solve for VB prime. In fact, VB prime is specifically equal to 2MA over MA plus MB. I didn't need to make that fraction bar quite that long, but that's okay. And now that is times VA. So I'll just put the VA on the outside so it looks like a dimensionless quantity multiplied by a quantity whose units are exactly the units of the answer that I want. So that's a good way of doing it. Of course, basically what I did to both sides of the equation immediately above is I divided both sides by MA plus MB. That's what I actually did to make this happen. So I've now taken care of this term. Now I got to take care of this term as well. So this one's going to be plus. In this case, we get MB minus MA over MA plus MB. Now, I don't really necessarily need those parentheses because the fraction bar is doing the same job. So I'll go ahead and subtract, erase those just to make it a little cleaner, if you will. So I've got MB minus MA over MA plus MB, and then all of that, of course, is just times VB. So this is, in fact, the general solution for the target particle's velocity after the collision in a one-dimensional elastic collision that conserves both kinetic energy, of course, and momentum. Now we're going to do part VB. We got to solve, or excuse me, now we're going to use VB prime to solve for VA prime. And we already had that equation 1 was equivalent to saying that VA is equal to VA prime is equal to VA or VB prime. So I'm going to go ahead and write down this 2MA over MA plus MB times VA plus MB minus MA over MA plus MB. I can put parentheses around that too, and that'd be VB. So now I've just accounted for, in this equation, I've only accounted for the VB prime. Now I've got to do plus VB and minus VA. I can see the denominator is MA plus MB, so I'm going to go ahead and make a common denominator while I'm at it. So instead of just adding VB, I'm going to say plus MA plus MB over MA plus MB, and all that will be multiplied by basically the VB that we were adding. And now we're subtracting a VA, but again, I'm going to go ahead and get a common denominator, so I'm going to say minus MA plus MB over MA plus MB, and all of this will be times VA. Again, that's because we're just adding a negative VA, but to get a common denominator, I multiply by 1 such that it's MA plus MB over MA plus MB. Now we've all got common denominators, and we've got a VA term and another VA term that we can combine. We also have a VB term and another VB term we can combine, and that's what I'm going to do is I'm just going to think about combining them. I can see now that when I add the 2MA, which is being multiplied by VA, when I add that to negative MA, negative MB, which is what's going to happen, then I get, as you can write here, 2MA, and then it'll be minus MA, and then it'll be minus MB. And all that is still over MA plus MB, and it's still being multiplied by VA because that was the term I was taking into account. So now I've accounted for this term and this term. Now I've got to account for the VB terms. To account for the VB terms, I'm just going to put a plus, and then I'm going to write M B minus MA. That takes care of the first term. And then there's a plus in front of the second term, or which is technically the third term, but it's the second term in VB. There's a plus in front of it, so we don't have to really distribute anything but a plus 1. So this is going to be plus MA and then plus MB. And then, of course, the denominator is still MA plus MB. And then we have all that times VB, and now we've taken care of this guy and this guy. So we've now done everything, and I'm finally in a position where I can go ahead and write the final answer. The final answer is VA prime is actually equal to, notice the 2MA minus MA just becomes MA, so it's MA minus MB over MA plus MB, and all that is times VA. So you might want to put it in parentheses, but you don't have to. Plus, now when I combine all that, I see an MB and an MB add to give me 2MB, but a MA and a negative MA add to give me 0. So this one's just going to become 2MB over MA plus MB. And then, of course, all that is times VB. And that's it. This is exactly the expression that your book suggested was the general solution for all or one-dimensional head-on collisions. So now we've done that, and you've seen the major tricks that we do algebraically to solve for collisions in one dimension. Specifically in this case, kinetic energy is conserved and momentum is conserved, so it has to be one in which the net external force is 0 so that momentum be conserved, and it has to be an elastic collision so that kinetic energy can be conserved. But that's it. Hope that helps you a little bit, and I'll be making another part to the video as well, but this is enough for part 2. Have a good day.